Welcome back to the course in Nuclear Medicine Physics. Today we have a short lecture on silicon photomultipliers. This is a relatively new technology, and the way in which these photomultipliers work is that they use semiconductor materials. In practice, they're easier to use than classical photomultipliers, which are bulky and require a really high voltage to operate. Anyways, enjoy.
Okay, so you've heard Arman talk about photomultipliers, and this was basically a device that is connected to a high voltage, and when a photon coming from the scintillator reaches the entrance of the photomultiplier, it releases an electron that, because of the difference in voltage, it goes hitting different diodes, and every time an electron hits a diode, it creates more free electrons, and we amplify the signal in this way until we're able to measure an electric pulse that has been a little bit amplified from just the initial low emission of light from the scintillator. So if you think about that old technology, for example, you cannot put these photomultipliers into a magnetic field because that magnetic field is going to deflect all those electrons. So if you're thinking in applications like, for example, building a PET MRI machine where there's a very big magnetic field, well, we're not going to be able to do that. So there's this modern technology you call silicon photomultiplier. Well, I wouldn't say it's super modern. I mean, the idea has been there for a while, but it's just more or less in this last decade starting to gain uses in nuclear medicine. And what are silicon photomultipliers? Well, now these are some photodetectors made of arrays of many little single photon avalanche diodes. We're gonna get into this diode thing in a moment. They can be configured in an analog or digital way. And the idea is that when a photon reaches a diode, then there's some electrical signal that is emitted. So similar to the normal photomultiplier. These silicon photomultipliers are very sensitive to photons. They have a very, very good spatial resolution, and they have a very, very high timing resolution. So of course, for application in nuclear medicine, that's very good as we're seeing. So what exactly is a diode? And this is the basic property of a diode. So you basically, well, in principle, in particular, we're going to talk about silicon, but silicon forms crystals with each atom having 4 covalent bonds with its neighbors. So basically, all valence electrons are used, so no carrier charges are available. However, if a small fraction of silicon is replaced, and this little replacement we call this doped, that's how we refer to this in solid state physics, with a valence 5 atoms. So for example, I'm showing some examples of atoms that you can use for this doping. This makes an extra electron available. So if there's more electrons, then we call these negatively charged. So it's called an N-type because of negative type semiconductor. But then there's a small fraction that can be replaced with a valence 3 atom. And again, a couple of examples of valence 3. So in this case, we are missing electrons. So there's going to be more positive charges. And these positive holes, because we think you can put an electron there, so that's how it's seen as a hole, is what creates a p-type semiconductor. So let's think what happens when we put a p-type semiconductor together with an n-type semiconductor. So the p has some positive charges, so an excess of positive charges. The n has an excess of negative charges. So in that junction, what you have is some of these negative charges from the right side are going to move to the left, and some of these positive charges are going to move to the right. And this creates a little zone in the middle that we call the depletion zone, because basically these charges recombined, and then we have no net charge in the middle. So this is what I just said. But then you can think, okay, what we use for silicon photomultipliers is something we plug in this diode in a reverse bias configuration. So basically the N-type semiconductor, which is negative, we're going to plug it to a positive side of a battery or of our voltage. We're going to put it at a higher potential than the positive semiconductor. So when we do this, this creates an electric field moving towards the left. So well, when we do this, the depletion zone, it grows a little bit. And in principle, when you plug in a diode in this reverse bias configuration, there wouldn't be any current flowing through that diode. What happens is that then when ionizing radiation hits the diode and it goes through this depletion zone, that remember is basically neutral atoms there, it creates ionizations. And then because those ionizations, because you have this reverse bias, this electric field moving to the left, when those charges are now free, the positive charges move to the left because of the magnetic, so because of the electric field, the negative charges move to the right, again, because of that reverse bias. And when we have this movement of particles, we can detect a signal, we can detect a little current. Now you can apply different voltages again to this diode. So if you start from a little bit, maybe you get a little bit of a signal. And similar to when we talk about gas detectors, the more we increase the voltage, then we're going to have different ways of responses for those gas chambers. Here again, we use a high voltage. And when you use a high voltage for the silicon photomultipliers, what it does is these particles that are moving gain enough energy to also cause extra ionizations in that zone. And then those extra ionizations basically create an avalanche of charges moving. You then have to stop that avalanche, and methods of stopping that avalanche is called like quenching circuits. But the quenching circuits, what they do is basically you reduce the voltage a little bit just to make sure that everything stops. But what we're interested in is we measure that electrical pulse, so we know that a photon interacted here, and then we're able to expand and process the signal. There are configurations in which it will allow you to detect individual events, or also to detect a pulse that is proportional to the energy of the initial photon, which is what we're interested here. We want to be able to discriminate high energy photons from low energy photons. We want to be able to discriminate the photopeak emissions of technetium from, let's say, the Compton scatter photons. We only want to look at the photopeak. And a way of doing that, there are several ways, but one way of doing that is you create an array of diodes. So it will look something like in this diagram there. So each little square there has many of these diodes. And because in the digital, when we look at this from the digital point of view, a digital is basically either the diode gets a current or it gets no current. So it's going to be a 1 or a 0. But if we get a 1 or a 0, how are we going to know if it was a very high energy photon or a low energy photon? We won't really know because it's just the same 1 and 0s. So what this array does, though, is a higher energy photon basically excites more of the diodes in the array. So we get a sum of multiple ones. So at the end, we're going to be able to measure a higher pulse of a signal that if it's a lower energy photon, that probably won't excite as many of the different diodes in that array. And that's basically the concept of how we use silicon photomultipliers. We were able to get a higher signal. Now, this is a solid state detector. So again, we've seen it can be more sensitive. It can be better high energy resolution. I wanted to point you guys to, I like this review paper, and it of course goes more into the details. It also talks about these silicon photomultipliers in an analog way, silicon photomultipliers to just measure single events and so on and so on. So I encourage you guys, if you guys want to learn much more about these silicon photomultipliers, definitely take a look at that paper. And this is how these new technologies look. So the old technology, what Armand described in the previous talk, yeah, this is how, this is how that photomultiplier looked like. So you have your scintillator, and that scintillator is coupled to a photomultiplier. Now, the new photomultiplier arrays look like what I'm showing here. So we have the crystal that is coupled to the photomultiplier. So when we get those emissions in this crystal, they excite different diodes in this array that then we process with the electronics. And this is what's coming for new PET and SPECT cameras. Yeah, so that's what we wanted to add. Now you think here you are not moving all those electrons in the vacuum between a difference of potential from dynode to dynode. Here is just everything happens in that crystal. So we can now put these type of detectors in a magnetic field, and we can now then start building machines like PETMRs and things like that. So it's definitely good technology, and it's gaining more and more popularity in nuclear medicine. So we wanted to just briefly show it to you. Thank you.